Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's truly a privilege to be sharing my thoughts today with such an elite and distinguished audience. I've had conversations with many of you today, and it's just an amazing group of people, so thank you all for attending the talk. Thomas Kuhn, in his classic book, The Structure of Scientific Revolutions, coined the term paradigm shift. As he described it, scientific communities function within a paradigm, largely making incremental advances within that shared, understood paradigm until there is a sudden and unpredictable shift to a new model or paradigm. Within computer science, we don't have paradigm shifts caused by incomplete theories of the underlying laws of nature. But we do have paradigm shift caused or driven both by technological limitations and large disruptive shifts in technological capabilities. Okay, I've got the notes. There we go. Okay. So for generations, people have been building software applications that have largely been able to ignore the low-level details of the underlying hardware. Okay, this speedboat here on the slide represents, computer science blasting along, more and more capabilities every year, making great progress, enabling applications, software, new science, new discoveries, all the things that we've been hearing during this faculty summit. Today I will argue that we're moving into an era where the physics in the underlying hardware will drive a paradigm shift that will affect many or most researchers in the field eventually. Okay, and for my architecture and hardware colleagues in the audience, I apologize. Many of you will be familiar with these concepts. I aim this talk at a general computer science audience. Okay, so the beast from below is transistor scaling, but I think there are opportunities to defeat the beast from below if we work together across the boundaries of the field. And that's what I'll talk about today. Okay, so we have the standard computing stack. Pat loves to give this in many of his talks. And we start at the bottom with devices, and I don't mean devices like smartphones. I mean silicon devices, transistors, memory cells, and whatnot. We're a devices and services company. But in that sense, Microsoft means the other kind of devices. And then you build circuits out of devices, and then you have microarchitecture, which is logic. Architecture on that, and ISN means instruction set architecture, systems architecture, and networks. And then on top of that, you compile down to them. And then, of course, there's a boundary that programmers typically use to write programs to this underlying stack. Okay, and on top of that, of course, you have how you figure out the algorithms that you need for the applications that you want. But what's been really important for productivity and for us to make the enormous progress we've seen over the past 5 decades is that the lower part of this stack has produced consistently large exponential gains in capabilities. I mean, year after year after year after year, things just get faster and more efficient and faster and more efficient, largely invisible to the layers above. Now, if you need a level of performance which is well beyond the capabilities of today's systems, you might wait, or you might build yourself a supercomputer. Both of those take some time. But the important point is that the incredible complexity underneath that line, all of the compiler transformations and optimizations, and all of the new features added to the instruction set architecture, and now billions of transistors in the microarchitecture, and the physics of those individual circuits and devices are hidden from the software developers to first order. And so we've been able to move orders and orders and orders of magnitude largely under the covers. And that's really what's enabled these enormous gains in all of these different capabilities and this vast increase in productivity. So that's the world we've been living in for the past 50 years. Okay. Now, the glory of Moore's law is that it has been the fundamental driver of these capabilities. And I can't emphasize the importance of Moore's law enough. And I think we all understand how important it's been. But it's been so consistent for such a long time that we almost take it for granted. And a little bit like the Japanese yen, which is called the widowmaker trade in currency speculation, predicting the demise of Moore's law has been a fool's errand for decades. Right? There have been papers proving that it can't go on much further, and then, of course, the proofs had a flaw, and it keeps going. And so, we almost take it for granted. And Bill, in his keynote this morning, talked about how programming today isn't really all that different. Of course it's different, but fundamentally, it's the same model as we had decades ago. So really, this has been largely invisible. Okay, so everyone knows about Moore's law. Less commonly understood or known about outside of the hardware fields is Dennard scaling. So Robert Dennard and his colleagues at IBM in 1974 published a paper that laid out a set of scaling rules. And basically what these said is, okay, you're going to shrink a transistor from one generation to the next. Here's how you shrink a transistor. A transistor is just a switch. It conducts current, with an on-off switch called the gate, a lot like a light switch. The gate is the switch that you toggle. And then current will flow across the transistor or not. And when you make them smaller, he set out a set of scaling rules where you scale everything proportionally. You scale the length by a factor of k. You scale the width by a factor of k. You drop the voltage by a factor of k. You increase the dopant atoms in the channel by a factor of k. K is typically 1.4. And if you follow all these rules, you get a couple of really nice features. Number one is that you keep the strength of the electric field across the gate insulator constant. So that's the constant that he drove to keep things going. And you'll see down at the bottom there that power density stays at 1. So you shrink transistors, you pack double the number of transistors into an area, and power density stays the same, even though you're driving those circuits a lot faster. So it's almost like magic. You follow Dennard scaling rules, you get double the transistor count, the individual transistors get 40% faster, and they're 50% more efficient each, giving you a constant power density. And that's every time you turn the crank, which is pretty awesome. And again, that paper was 1974. We had about 3 decades of Dennard scaling. Okay? So this is really the underpinning rules that enables Moore's law. Because if you didn't have this scaling, you'd be in trouble. Okay, so what's the catch? Well, there's a little problem in that Dennard scaling is dead. Okay? It's failed. And the reason that it's failed, I'll go into in a moment. If we look at the axes, you see the transistors on top in red. And this was a really nice graph put together by my colleagues at Stanford, Mark Horowitz, Kunle Lukkerton, and others. Moore's law is alive and well. It's cranking up, doubling of transistors every generation. And then while we were on this train, we saw in blue single-thread performance kept increasing, and the clock rates in green kept increasing. And you see the divergence between clock in green and single-thread performance. That difference is ILP, instruction-level parallelism. But basically, we were getting exponential gains in single-thread performance and exponential gains in frequency. And people were juicing extra power to drive things faster than the efficiencies that Dennard scaling gave you because they wanted the performance because there was such a big economic incentive. Okay? But what happened was that the gate insulators got so small, the oxide thickness, small numbers of atoms, that it really became impossible to scale anymore. And so you couldn't drop down the threshold voltage and thereby the supply voltage without generating a lot of leakage. It's like for your light switch analogy, it's like you buy a new light switch and either the light is always a little bit on, even if you turn it off, or you reach and touch the switch and you get a shock. Okay, neither of those are desirable. So if you tried to follow Dennard scaling rules past the point where it failed in the mid-2000s, 2004, 2005, you're just dissipating more and more current even when the transistor's not doing anything. It's called leakage or static power dissipation, and it's no good. Okay, so that really drove us to a non-regular or non-uniform scaling, and that's created all sorts of problems. Okay, now if you shrink the transistors and you you pack the transistors much more densely, but you don't get the corresponding energy efficiency, what you see is that power density starts to climb, and you're consuming more and more power in a smaller area, which is more heat. And so there's really only a few ways to handle this. You can just keep powering the chip more and more, and driving more and more cooling. You can just hold off on power and leave the chip underpowered and not doing as much. Okay, but you don't really have a lot of good options. And so as a response in the mid-2000s, we saw industry go and shift to multicore to try to extract more efficiencies out of the transistors that they could power and keep driving performance forward. And that was a major shift caused in part by this failure of Dennard scaling. Okay, so is multicore the answer? There was a consensus in my community around 2008, 2009 that multicore was going to save us, that it was, we were just on this path of scaling cores, and they'd double every generation with the transistor counts, and pretty soon we'd have chips with 1,000 high-performance cores on them, and everything would be fine and dandy. And as long as we learned how to do efficient parallel programming, we'd be fine. Of course, that's very hard. So I was really interested in this question, and so my group and collaborators published a paper in ISCA 2011 that talked about both dark silicon and the feasibility of multi-core scaling in this power-dominated area of disproportionate transistor scaling. And the question we asked is, what happens to multi-core performance when you're packing more and more transistors on the chip and using them to generate or increase the number of cores, and then you can't drive them as fast because of the power limits? So what do you actually get? Okay, and I should say that in this era, even when you're power limited, because we have these cores, work on better parallel programming, better parallel languages, more efficient parallel architectures is still really important because it gives us extra performance for free. Just like work on single-threaded performance is still really important, and work on energy efficiency for single-threaded performance and parallel execution is still really important. All of those are, in fact, even more important now because we're not getting the freebies out of the transistors. Okay, so there's just an enormous amount of great work going on in parallel programming, a lot of it being done in MSR's collaborations with Berkeley and other places, and that work remains, I would say, not even as important as it was, but more important now. Okay, that being said, we did a study that said, given some different technology scaling assumptions, how much were we going to get out of more cores? Okay, and so the vertical axis there is speed up, basically how much performance do we get given a fixed power and area budget, and then the x-axis is years. The blue line is actually historical performance brought forward. So that's what we got in the last 10 years. So meeting that line would be doing as well this decade to come as we did in that past decade. And we made two sets of technology scaling assumptions. What we call ITRS scaling, that's the Semiconductor Industry Association that puts out a roadmap about how well we're going to do. And their projections, I think, are way optimistic. And in fact, we're starting to see that now, that they've been much too optimistic as we've fallen off of this curve. And then the line below it is what we call realistic scaling. And it looks really like that's what we're tracking now. Okay, so with maybe small changes, but we're pretty on the mark on that one. And so over 10 years, if you're following the realistic scaling curve, 4 parallel applications, assuming that you have the optimal multi-core topology for each individual parallel application, you get a speed up of under 4 over 10 years. Okay, and historically the speed ups have been higher than even 18x, but we started to slow down in the last 10 years. So this really says that there's really not that much juice left in multi-core. Now that's absent. There could be a big breakthrough in transistors. Certainly that's possible. There could be a great breakthrough in architecture or parallel languages that give us 99.9% parallelism. So there are things that could happen that would shift this curve up. Okay, but given a set of fairly optimistic assumptions, we're looking at this. So now there are a number of ways to deal with this problem of having too little power to power your whole chip. Okay, and there's really 3. One is that you can say, well, I'm just gonna burn the power and build an expensive cooling and have liquid cooling in my PC and then my pocket. Okay, there's some economic challenges with that, not to mention a different kind of leakage. We could decide just to turn off part of the chip and leave it dark. This is why people talk about this being dark silicon. And part of the chip stays lit. And so you just switch over to whichever part of the chip you need, and you build 1,000 special purpose accelerators, and you just light up the 5 that you need at any one time. Okay, we call that Frankenchip. It doesn't sound very productive for software. That's a second option. A third option is just to make the chips smaller. And if you make your chips smaller on a nonlinear scale with each generation, you have an explosion in supply and not much of a jump in capability. And that really changes the economics of the industry. Okay, and I think we're going to see the third option being the most likely. All right, so that's also going to put some pressure on silicon scaling. Okay, so all this multi-core work is really important, but it's not going to be the driving force generating the sort of gains that we've seen in the past. At least that's my belief. Okay, so I thought it would be interesting just to give some context and take a look at the past to see how we got here. So, I mean, these aren't anybody's names other than names I thought up for this talk, and I'm sure they're not entirely accurate. But, you know, you can think of the late 30s to through the 40s with, you know, Eckert and Mauchly and Turing and von Neumann. It's what I call the age of discovery. This is when they discovered not only a lot of the results about computability, but really laid the foundations of the execution models that we're dealing with now. The stored program concepts, von Neumann computing, instruction fetch, all of this sort of thing, you know, was really laid down by these giants in this period. So this was, as one of my colleagues said, you know, an era where giants walked the earth. And then, you know, in the late 50s through the 60s and early 70s, what I call the era of invention. These are things when a lot of the basic concepts that we take for granted were invented. Things like caches, you know, out-of-order execution, virtual memory, stable instruction sets so you can reuse software from one machine to the next. You know, these were all developed in that period. And then, you know, starting in the late 70s and through the 80s, we had an era of integration where we started building single chip computers, which at first were microcontrollers, and then we pulled more and more stuff onto those dies. And then once we had integrated the things we knew how to integrate, caches, floating point units, we went to an era of ILP. We started going to out-of-order execution, deep pipelines, very fast clocks, and drove the performance of these, what at the time were called killer micros, way up. That ran out of steam because of Dennard scaling, as well as we hit a lot of limits on efficiency, and we shifted to multi-core. And I think that multi-core shift, you know, starting in about 2004, will really have run its course, you know, in the next couple of years, 2016 or so. And so the question is really what comes next? What are we going to use to drive this next big wave of computing? And this is the paradigm shift that I'm asking about. You know, where is this next level of performance and efficiency going to come from? Okay, and that's what I'll talk about in the rest of the talk. So there are certainly some candidates. One is that we can start specializing logic. Neural computing is a great candidate. I'll talk about both of those. My wonderful colleague Krista is going to be talking, you know, is talking about quantum, and that runs very cold. Interestingly, Dennard, in a recent paper, said that you can actually keep scaling the voltage if you keep scaling the temperature down with it. Okay, so you know we go to minus 50, minus 60 centigrade, That provides a scaling path. It provides takes some other challenges and engineering feats too, and is not something I want to have in my pocket. Okay, but this era of X, what X is a really important question, and it may not be just one thing, but it's coming soon. And I think that's the message that I'd like to convey today, that we really have to work on figuring out what X is, and X is going to require breaking a lot of the traditional barriers down. Okay, so let me start the first candidate, which is specialization. So it's well known. This is a sort of a classic graph that's widely used that Bob Broderson at Berkeley put together a while back. He took a number of chips from the ISSCC proceedings between 1997 and 2001 and categorized them by function and efficiency. So on the y-axis, you basically have energy efficiency, and on the x-axis, you have they've sorted the processors based on how efficient they are. And the category in the left is general purpose microprocessors. These are the things that are nice and easy to program, and they run everything. They just run everything very inefficiently. But as long as the party's still going, we don't care. Okay, digital signal processors in the middle, they get between a factor of 10, 50, 100x efficiency. And then dedicated hardware, or ASICs, application-specific integration circuits that do one function, run between a factor of 100 and 1,000 more efficient than a general-purpose processor. Okay, so by specializing the logic just in circuits to the function that you want to execute, you can already reap large gains in efficiency over where we are today. And this is no surprise. This is well known in the computer science community. Okay, there are a couple of intermediate points, though. ASICs, are, like I said, are up there at the top. There are FPGAs, which are really interesting devices that are basically programmable logic. So they express their logic not in and or gates mapped down to transistors, but in lookup tables that express logic functions, and you can wire together a whole bunch of lookup tables to generate larger and more complex functions. And these give you, a jump of, say, 100x over a general purpose core, but they're reprogrammable. But you pay a factor of 10 over an ASIC. Okay, so there's some really interesting possibilities there. Now, I think as I alluded in the last slide, there are more gains the lower you go. And the last graph was really useful for understanding the disparity of efficiency on existing chips. But let's understand the space of possibilities as we start to think about specialization and new execution models. Okay, so I think of code specialization as giving you potentially an order of magnitude. And obviously, these are very rough numbers. Code specialization is things like taking a multi-core chip and rewriting your single-threaded application to run over 16 processors. If you do it well, you might get a speed up of 10x. Okay? And this is on a single machine. Obviously, if you have many machines, the gains are potentially higher. Okay, logic specialization, as we saw on the last slide, can give you another order of magnitude. Okay, so by customizing your circuits, you can maybe go down to a factor of 100 or more over general processors. That's a lot of work. Okay, and we don't have any way currently to do that productively. If you go down the next level to circuit specialization, you can start doing things like analog circuits that are not Boolean gates, but are representing actual functions. These, of course, you're starting to leave the digital domain. And, of course, there are some things you can do and stay in the digital domain. But there's another order of magnitude there. And when you start going down into devices, using actual small devices that compute different functions, there's even another order of magnitude there. Okay, so if you're looking at ion mobility in an ion transport memory, which is 10 nanometers across, they have some very interesting properties as a function of the current flowing through and the resistance and the state of the cell. Okay, so we can build devices that give us a lot more. But right now, we have no way to specify them or use them at higher levels of the system. Okay, so the first two layers, I would argue, are sort of what we understand. They're Boolean, they're digital, they're easy. They're hard to do well, maybe. But down at the lower levels, that's where the big gains are. Okay, and the question is really, how are we going to marry those lower levels up to the software stacks that have been so productive and so stable for so long? Okay, so starting with logic synthesis, going down to that second order of magnitude by specializing the logic. There are large gains in efficiency if you can start to specify your software functions down on logic as opposed to a general purpose processor. Now that becomes a spatial thing. I mean, you're not running a function through a stream of instructions through a processor. You're actually laying down the code completely concurrent, data flow like on a collection of communicating state machines where everything is running at once. It's fundamentally a very fine-grained concurrent language or model. And again, 100x for FPGAs or something called coarse-grained reconfigurable arrays, which are more like spatial arrays of functional units connected with various types of networks, than 1000x for ASICs. But the development and compilation for specialized logic is an enormous challenge. I mean, people have been at this a long time. We've made slow progress. But what's really interesting and starting to change is that these fabrics of programmable logic are no longer just the raw logic lookup tables that you have to put a circuit down onto. The major vendors, Altera and Xilinx, there are a host of other companies working on this, are now starting to put down things like functional units, clusters of functional units in a sea of reconfigurable logic around them. And they're starting to stamp out processor cores with a sea of reconfigurable logic and functional units around them. And memory blocks with a sea of processor cores and functional units. So we're getting this very interesting stew of cores and programmable logic and functional units and memory blocks. And it's a substrate that's much richer than the old kind of standard, just here's a bunch of programmable gates. And there's a lot of work going on in tools to map down to that. Altera has a stack called OpenCL, which is really a standard to map kind of data parallel types of languages down to graphics and other accelerators. And now they're targeting this interesting stew. Xilinx has a product called AutoESL, which is much more kind of logic programming coming up and trying to make you more productive. And whether they meet in the middle or something else comes and provides productivity is a really interesting question. So we see really interesting mixes of these functional units and these tools in this stew. So I think we're going to see some breakthroughs here. I think we're going to start to see wide adoption, and maybe in niche areas at first. But this will be a candidate for getting us past some of these challenges that we're seeing on the scaling domain. And then I think, given how fast workloads change in the cloud, we're much more likely to see programmable logic there first, and then things like CGRAs or many more types of ASICs in the client, which need that extra energy efficiency and have sort of more predictable workloads, since you're replacing the devices and not rolling out new services as often. Okay, so that's specialized logic, but what is the challenge here? Well, it's got great potential in the short term. We have a lot of challenges at the language and algorithm and application barrier. I mean, exposing this to software programmers has historically been very hard, but it's a problem we have to tackle. And we need help, we hardware people need help from the higher levels of the system in figuring out what sort of concurrent languages can actually make this productive. What libraries and data transport frameworks and fabrics can we use to sort of select a flow from a pre-orchestrated library and then plug a bunch of kernels in. But it leaves these other two levels unaddressed. There are field programmable analog arrays, but they're really niche right now, and this says nothing about devices. And this is where the big speed-ups are. Okay, so what can we do to attack these levels? There's another issue here, which is that in the logic specialization space, you have efficiency, you have a spectrum, and you have efficiency on the far right. Okay, ASICs at the extreme. You have generality, what we think of as CPUs, on the far left. And you can think of that as inefficiency in the extreme. And then going from left to right, of course, we start with CPUs, then you have multi-core CPUs, and then many-core CPUs, and then GPUs, and then FPGAs, and then ASICs, right? So the farther right you go, the less general you get, and the more work it is to map, but the more efficient you get. And this tension is not something that we know how to resolve today, but we need to make progress. So I'm hoping that these software tools for mapping down to these interesting substrates will help us to make a lot of progress. But how do we resolve this tension in a more fundamental way? Or what is the hook that's going to give us an added advantage that we didn't have before? Because people have been at this a long time. Okay, so a final comment, is that if you look at Moore's law, and thanks to Shekhar Borkar at Intel for this chart he gave me a while back, we're currently at 22 nanometers, moving to 16 or 14 if you're Intel. For reference, a silicon atom in a matrix is about 2.5 angstroms. So we're looking at, think of 4 per nanometer. Okay, so by the time we get down to 4 nanometers, we're looking at transistors that are 16 atoms across. Okay, that's the long way. The short way is the gate on top. Okay, so there's an economic imperative to extract performance from these generations of transistors. We're not getting the free scaling and energy efficiency anymore, and the power density is climbing. In addition, we're starting to pay more and more of a tax for the digital abstraction. Because these transistors are getting leakier, they're getting noisier, there's more variance, they fail more often. Okay? At each step you take down, you're getting closer to the atomic domain, and we're pretty close already. And things just get very, very tough down there. Quantum tunneling, high velocity electrons, process variation. You're manufacturing, hundreds of billions of transistors, okay, with small numbers of atoms. Okay, so we pay a fairly high tax to get a clean digital representation with enough band gaps to keep things functioning as they should be. And the challenge is that at some point along this road, as you get down to single atoms, that tax becomes too high. Okay, you're not going to build a stable digital transistor out of a single atom. Okay, and so at some point here, that tax becomes too high, and if you don't figure something else out to do with those transistors, that stops the scaling. So I think we hit an economic end long before we hit a physics-based end. We may be able to manufacture them, but we have to be able to extract value from them to justify the tens of billions of dollars that you need to move to the next process node, because every node is getting harder. Now during this time, so this is sort of the danger zone as I see it, I'm guessing 11, but probably 8 is where we're going to run into serious economic challenges without some new model. Okay? During this time, of course, DRAM is likely to die, but that doesn't mean progress is over. We're going to be making a lot of progress on denser non-volatile technologies, 3D stacking, integration of multiple technologies into a package. So there's going to be a lot of stuff happening through this, and even after Moore's law is quote-unquote over. So it's not an end of progress, but the question is, how do we harness these nasty, noisy devices in a way to provide better performance and the economics to keep scaling going as long as we physically can? Okay, so I think there's an opportunity to break this digital tyranny, okay, of this abstraction of ones and zeros that served us so well for 50, for 60 years, okay? And that's to embrace approximation. Some people call it analog, some people call it approximation. Okay, this is, there's a lot of great debate going on in the community right now. We've tried this, it's too hard, it's black magic, okay? But the world is different now. Not only do we have an enormous economic incentive, our workloads have changed. We're doing enormous numbers of things that intersect with the analog world, our world, in fundamental ways. And so if you look at that list of applications, or classes of applications, large-scale machine learning, vision, bioinformatics, mining big data, speech, AI, NUI, these are all things that take, in some sense, an analog input or produce an analog output or have many possible answers. These are things where you can afford some imprecision. These are things where you can afford some error. In fact, you can afford a lot if you have the right algorithms, if you have the right convergence. Okay, as an example, my group is working with a very interesting workload internally that we're trying to accelerate. We had 400,000 thresholds in this workload, represented as 32-bit floating point numbers. And we wanted to make it more efficient. So we just did a quick thing. We just took all but 1,600 of them, so 398,400 of those thresholds. We just dropped them to 20 bits. Okay? The other 1,600, we said, oh, those look big. We'll leave them alone. We won't even try to mess with them. And we saw no reduction in the quality of our output. Okay? We don't actually know how low we can go. And I'm guessing for each of those, for each of those thresholds that's carving out a different part of the space, it'll be a little bit different. We have no formal way to deal with that. Right? We don't have the models, we don't have the mathematics, we don't have the language support. We're doing this all by hand and by trial and error, and it's really time-consuming and messy. But there's a huge opportunity there. We just dropped the precision by a third for almost all of them, and it was free. Okay, this is no surprise to people that work in machine learning, right? Sometimes you need single precision floating point, sometimes you need double, but very often you need far, far less than that. Okay, so these workloads can be very robust to reduce precision, and they can allow us to start computing with circuits and potentially eventually devices that are far more efficient than what we have today. But we need the right abstractions to reason about how much error can you tolerate, how much noise is acceptable, what function are you trying to drive through, how do you map that onto the functions, how do we characterize their distribution, what if we have dynamic noise, how do we manage all this? And right now we have no idea, okay? But the potential is there. There's huge opportunities. The workloads are amenable, but we need help from across the stack, okay? And I'd like to point out that this is both this approximate computing work as well as the work I'm about to talk about was in close partnership with Louis Cezay at University of Washington, who has a great program in approximate computing. He's really driving this work. Hadi Ismailzadeh is our student who did a lot of the work, Adrian Sampson and others. So thanks to them for giving me some of the material on the slide. So if I think about approximate computing and energy efficiency, here I show a Pareto frontier. On the y-axis I have energy going up as we go up, and then performance going to the right on the x-axis. And you can take a bunch of processor designs and compute that frontier, and you can always buy a little bit of performance for a disproportionate more energy, right? It's a nonlinear curve. So if I want that extra little bunch of performance, it's going to cost me some more energy. And so we, of course, try to move down and to the right with better designs, more efficient architectures. That's sort of the bread and the butter of my community. But with this approximation, we have a great opportunity. We can add a third axis of error or imprecision. And now instead of a Pareto frontier, we get a Pareto surface. Okay? And the shape of this surface for each of these workloads is at this point completely unknown. All right? We have no idea how far we can push this. Okay? But once you're willing to take a little bit of error and you break, again, this digital tyranny, you can start using these devices that are noisy, and you don't have to pay that enormous tax to guarantee a 1 or a 0. Okay? Now, of course, there are points on the surface that don't make sense. Right? I mean, I can get 0 energy and infinite performance if I'm willing to take enough error. Right? I just pick a result, and I'm done with the computation. So clearly, that doesn't make sense. But there are a lot of really interesting points on this. So I'll talk about one kind of very incremental step we've taken in this direction next. And that's taking von Neumann computing and transforming it to neural networks. Okay, this was a really surprising result for us. We didn't think it would be this work this well. So on the left, and this is again, it's work with Luis, Ceze, Hadi, and Adrian. So on the left here, there's sort of a standard control flow graph of a traditional imperative program, C, C++, whatever you want. We find some target region which is well structured. So well-defined inputs and outputs, no side effects, a lot like functional programming. Okay? And then in our compiler, we actually have a unit that observes it. Okay, so we train a neural network. It observes the inputs, it observes the outputs. We run this over lots of input sets. We interpolate inputs and then run them through if we don't have enough input sets to work with. And then, of course, we test it against a real set after we train it. And what it turns out is that if you pick the topology of a standard artificial neural network, or ANN, based on the workload, you can actually do really well. You want a different topology for each one, of course. Obviously, if you give them all a giant topology, they'll be good in the limit, but then you pay a lot of inefficiency. For small functions, you can use a small topology. For really large functions, you need a much bigger topology with more hidden layers and more inputs and more and more neurons in the hidden layers. So we observe it at runtime, and then what you can do is that when you've transformed that representation into a neural network, then you can run it on an accelerator. And in the paper that came out in Micro last year in 2012, we proposed a digital accelerator that was tightly coupled with a processor pipeline called a neural processing unit, or NPU, marketing speak, because it's supposed to be analogous to a CPU. And the idea was that you take that neural network and offload it to the neural accelerator, which was digital and had all these properties. Okay? But the really interesting thing here is not that we can do this, but that across all these different types of programs, we can transform very different kinds of loops, with array accesses, dependence chains of instructions, into a common representation. And that common representation can tolerate some error, and that common representation maps these very different types of von Neumann code down onto a single substrate, which is neural. And so that was the real surprising observation, that across all of these application classes, I won't read them, but there are 6, and they're all very multimedia or robotics. All this new analog domain type stuff. They all were able to compile into a small space of neural networks. And so that common representation actually gave us very good results. So for these applications, and not just the inner loops, but for the whole application that we're doing these, we got about a 7x improvement in energy delay product. 2.5x speed up, 3x reduction in energy, just by transforming the mean kernel to a neural network and then offloading it onto a digital representation of a neural network. And I show you there the before and after of a baboon. And I'll take it out before you can see the differences. Okay, but they're small. Okay, so now if I look at the stack that we go back to, the problem is that the NPU gains are still limited. They're still less than a factor of 10 because they're hidden behind all our standard abstractions. We're paying for Amdahl's law. Okay, now we have some work going on now that's pushing those down into analog circuits. We're already incurring some error. That error is typically less than 10%. In all these applications, the quality of the output was not deemed to be so bad that it wouldn't be worth doing. Okay, it's subjective, of course, how much error, and that's another problem for people to work on. And then eventually we can push down into devices. And there's actually a lot of people looking at devices to support these classes of computation, but not NPUs specifically. So that's an example where just by relaxing this digital requirement and bringing in a little error, we were able to do a fairly significant program transformation that was able to map down onto either software with code transformation, logic specialization with the digital NPU, circuit specialization with the analog NPU, and then eventually devices like memristors or other things that do well with neurons and may compute a sigmoid. Okay, but to really take a jump past this, I think that approximate computing is the key for a lot of these workloads, and the numbers and the importance are growing every day, is the key that will lead us to some of these new execution models. I think as long as we require that we stay completely digital, it's very hard to beat von Neumann computing for efficiency or generality. And we can work on logic specialization, and I think that's what we should do in the short term. That's going to take us a fair ways down for efficiency, but it's hard. And right now it's very, very labor-intensive work for really talented people to make a lot of progress on. So, I guess my plea is and I know there are lots of people doing this. There's lots of people working on quantum here at Microsoft and elsewhere. I think the community is starting to do more and more with neural as a general execution model, which is really interesting. Hardware synthesis, a lot of people too. There are many other possibilities. And von Neumann was one of the co-inventors of cellular automata. Bayesian maybe for biological computation or representations. But I think we really need to think about new execution models that can map down on devices and then provide the abstractions all the way up, these new stacks that will let us get these factors of 10,000 or more that are achievable with these atomic scale devices before we run out of steam and just give up. Okay, and I think, like I said, I see a lot of really interesting stuff happening in neural networks, not just the work that we're doing to be compatible with conventional von Neumann computing as an offload engine, but people are now taking scientific applications and recoding them as neural networks. Olivier Tamam's excellent work from INRIA. There are many types of interesting networks. I mean, obviously, there's the old school ANN stuff, but then there's all the heavy emphasis now around deep belief networks, which at some degree are bio-inspired, I guess, because they're deep. And then there's the whole class of things that are bio-abstracted neural networks, and by that I mean actually trying to pick out what the fundamental primitives are from our brain that makes it work and discarding all the rest, getting the cleanest possible abstraction in connectivity, neuron function, role of neurotransmitters, and all of that, and topology, so that we can actually get the efficiencies that we get with this 20-watt part, with synthetic systems. And there are some really important discoveries to be made there, because no one really understands what that minimum set of primitives is. And Jim Smith is a giant in my field who's done just seminal paper after seminal paper for decades. And he made a comment in Tel Aviv a couple of weeks ago when we were having a summit. And he said that like the 40s, there are giants. He believes that there are giants walking the earth today who are building the underpinnings of these neural models that we will eventually use for widespread computation. We just don't know who they are yet. And so, maybe some of them are in this room. I know it's not me, but there are giants walking the earth. So I think that's really exciting. Okay, so I'd like to wrap up this with 5 testable predictions for 2025, given all this. And so looking ahead, given the trends that we've seen and all the various work going on in the hardware community, and in our related communities, what do I think things are going to look like in 12 years? Okay, so first of all, Moore's law will be dead. And by that, I just mean this regular cadence of CMOS transistor scaling every 2 years. We double the density. Okay, we'll still be making lots of progress. There'll still be lots of exciting work to do. But that end will transform our industry and our digital systems. It's going to really affect things, because none of us have ever worked in a world without it. Okay, and when you turn off a 50-year exponential, some surprising things are going to happen. Okay, I believe that hardware-software compilation will be common. This is along the lines of logic, specialization, and synthesis. So if you have a really demanding application, you're going to run it through a compiler, and it's going to spit out some hardware description language that'll be run through a synthesis tool, and it's going to spit out some software. And it may spit out one big glob of stuff that goes into this mush that I talked about of cores and functional units and IP blocks and reconfigurable logic. Okay, but that's going to be a radical departure, because that's kind of the easy thing right now. It's hard, but I think it's one of the clearest in terms of its value proposition. I think we're going to start seeing a complete stack around neural evolution and execution. So that stack, the abstraction stack, I think we're going to have one for neural execution. I think there are going to be well-defined interfaces at every level, from devices all the way up to algorithms and programming languages. I think physics-based computation, this is harder, and it's longer term, but it's going to be a really hot topic. So extracting stochastic behavior of atoms in different devices and trying to extract those functions and make those functions sort of higher semantic functions. This is the old RISC-CISC wars. We'll have CISC for atoms, okay? And people will be investing a lot because the potential gains are so high. So there'll be an explosion in people trying to create devices that have interesting new functions as the building blocks for some new physics-based model. And I think that's going to be longer term. And then finally, I think given where I see the neural stuff going, and I don't think this is surprising to anyone who's certainly working at MSR or attending the summit, the machines are going to be beating humans at many, many more tasks than they are today, whether it's speech recognition, vision, et cetera, et cetera. And this will be transformational, not just on our field, but on society. And I think we need to think very hard in reference to the question to Bill Gates this morning about the downside of technology. I'm an optimist too, and it's just amazing things we're going to be able to do. Somebody is going to have to take responsibility, though, and it can't be politicians for thinking about how we guard or gate the impact this has on society, because technology is now so pervasive and so powerful, and it's moving so fast that it will have, it's changing all of us. You go to the bus stop and you see people, everyone's staring into a little box, right? So it's changing us as we speak. And then I guess one last comment, since I have the podium. I worry a little bit that the publication requirements in computer science now are so onerous that it's very hard, especially for junior people, to take big bets. Okay? If you want to jump out and work on one of these new models, which is going to take a decade or more of very hard work, and you're expected to turn out 4 or 5 or 6 top flight publications every year, that's one every 2 months, it's really hard to kind of detach and do a lot of the fundamental work if you're expected to stay on that flywheel. And people do it. It's possible. But I worry that our publication requirements are so high that it may be inhibiting some of the really important long-term work that we want to see. And so something that I've tried very hard to do in my group is give people the freedom to publish when they have something amazing to say, and not worry so much about showing a certain rate of publication. And I'd like to see a lot more of that, because I think we have some really hard challenges ahead. I know in my community, at least the rate of requirement is just crazy. And it's been growing every year. Okay, so I really hope that together we have this great opportunity with devices, with circuits, custom circuits, approximate computing, analog, interesting new software stacks. Working together, I think we can define the new abstractions that will create the new stacks of the future and give us 3, 4, 5, 6 orders of magnitude more capability, and jump ahead to some of those grand challenge problems and great visions that the futurists dream of. I'm incredibly excited and optimistic. I think that we're going to get there. There's a lot of hard work to do, but there are at least some paths forward. Even though the traditional ways, that the free lunch is slowing down a little bit. So my hope is together with all of you, the software community, the language community, the algorithms community, we can all work together and we can turn that beast from below into something tasty and keep the party going. Thank you very much. And I see Jignesh with the first question. This is a longtime friend. We'll start with him.
Coming down, number 2.
Doug, that was a fantastic talk as usual. Great to hear from you. I have 2 questions. First one is, you talked a lot about how to make computing more efficient with the ideas you mentioned. What about getting data in and out of those computing devices? What do you see happening with memory buses to connect all of these to make it scale the way you are saying? That's the first question. The second one is, Wall Street has been doing algorithmic trading and rumored to have been using ASICs and FPGAs for 4 or 5 years. So should we be following the money and do what Wall Street does? I'm sure I'm going to go to hell for suggesting that we follow the bankers.
Okay, so let me unwind those. So for getting the data in and out, it's clearly very important. I did say I think we're going to see an explosion in non-volatile memory devices. And if you look at some of what's happening in the NAND space with flash, they're starting to build vertical chains of cells as opposed to horizontal stripes. So we may be seeing 4, 8, 16 layers. So there will be a lot of storage that you can attach to chips with through silicon vias and get very, very high bandwidth. The intersection of 3D stacking, silicon photonics with chips, I think, are going to give us tremendous jumps in bandwidth and capacity locally. And then, a lot of the new microsecond scale networks coming out in the data centers will give individual servers access to a much broader pool of storage, a flattening of the data center, if you will.
We need 4 or 5 or 6 orders of magnitude if we follow you down to 2025.
Yes. So there are a lot of technological directions we could take, and there's a lot of work to be done. I think all of those are promising. I don't know if there'll be enough. Okay. As far as following the bankers, I think they certainly have been building custom systems because the economic incentive is so high. Maybe by having us all build some of these tools and make it easier to do that, we can level the playing field and give high-frequency trading to the masses. Give the power back to the people. You just need an office within one city block of the trading floor, and you're good to go.
Let's take number 2 again, and then we'll take a question from the live stream. Number 2.
I'm Al Aho from Columbia. Tremendous talk.
Thank you, Al. It's a pleasure to meet you, by the way.
We had hybrid digital analog computation back in the 70s.
Yes, we did.
And one of the things I hope that you'll do is, unlike a lot of hardware designers who have inflicted upon us software people a hardware architecture that's very difficult to write algorithms for and compile into, the multicore arena.
Yep.
What will you offer us to make writing programs and compilers much easier for your vision of the future?
That's a great question. So the glib answer is I think we need to work together rather than having us inflict something up, because we don't really understand what those primitives need to be. You know, in the early days in the 40s and, the age of discovery, we were just working on stored program concepts and generating instructions, but there was no reusable instruction set. It wasn't until IBM had a research project in the late 50s to be able to reuse instructions from generation to generation. And then, of course, there were all the debates about compilers versus assembly language programmers in the 70s that you know much better than I do. I think the most important thing is to understand initially a set of primitives that we can expose up, and then think, once we understand the primitives, look at the compilers and the languages to think, how can we start stitching those together? There's some actually great work, if I do say so myself, going on at Columbia with one of my former students, Simha Sethumadhavan, who is actually starting to build those primitives, integrators to do integration, differentiation, multiplication, trigonometric functions out of analog circuits, and he's starting to think about how to push those abstractions up. So I don't have an easy answer for you, other than it needs to be, we need to start with the primitives, think about how we compose them, and then think about what those interfaces ought to be at the higher level. It's a hard problem.
And I think Simha's great.
Yes, thank you. So do I.
So let's take a question from the streaming audience. We've been live streaming this talk. Our proxy for the asker. How do you think, Doug, the changes in the hardware ecosystem will affect job opportunities in computer science in the next 10 years?
I think they will increase the job opportunities because there are going to be a bunch of really hard problems to solve and new technology spinning out. And if you look at the industry ecosystem right now, we have so much data and we have so many machines and so many advances, that people are building applications that take a combination of maybe new networking or new data or new uses, and they don't need that really cutting edge performance. So I don't think this is going to reduce in any way the demand, for example, web programming or software jobs. I mean, the digital ecosystem is marching through the economy, eating all these analog industries. Maybe it's a bad metaphor to use given the talk I just gave. All right, but so then we have to have an analog wave behind it. So that's what's driving a lot of the job growth in our field. And I don't see any signs of that slowing down. I just think that now we need to make the investments so that we have those new capabilities 15, 20 years from now. Because any of this stuff, even in architecture, architecture is such a weird field because it's a deep funnel. You come up with an idea, in a general purpose core, it might be a small idea, you put it into the funnel, 10 years later, if you're lucky, it comes out the other side, but then it gets applied across billions of people. I mean, what's the value of 1% across all of computing? It's huge. But it's a long funnel. And so I think the stuff we're talking about now, we won't see in production for 15 or 20 years, and we just need to make those investments now.
Thank you.
There's a question.
I think we've got time for one more question, then we'll go to the buses. Number 2, please.
Yes, so is this on? So is there any reason in particular that the approximate computing idea that you were mentioning couldn't entirely be done in software, where the hardware and essentially the bitwise computing is still entirely precise? And in recent years, there are, of course, many examples of this. Nobody, for example, would do lossless video and audio compression. People always do lossy compression. And so in some sense, maybe the approximation could stay within the software, which is entirely what happens in, for example, machine learning and optimization and many other approximate algorithm fields.
So that's a great question. Thank you. The question was, why can't we just limit approximation to that highest level rather than paying all of this pain going all the way down? And I think the answer is that if you go back to the stack of code specialization and logic specialization and circuit and device specialization with an order of magnitude jumping at each, I think what you're talking about is code specialization, where you can come up with algorithms that exploit that approximability to reduce the computational overhead or the number of discrete computations you do. And of course, when you look at, if you look historically, for example, scientific computing, over the years, they've seen 5 to 6 orders of magnitude growth in hardware capabilities, and they've gotten 5 to 6 orders of magnitude from algorithms. And the algorithms are still incredibly important, and that they actually talk about 12 orders of magnitude, half from the systems and half from the algorithms. So anything you can do at the hardware level, at the software level, to make yourself more efficient is fantastic. But then when I talk about going from 32, for example, to 20 bits, or reducing the bit width, you don't have the primitives on a digital processor to do that. You need logic specialization to exploit those narrow bit widths. For example, where FPGAs really, really shine is when every computation has a different bit width, and you strip out all the stuff you need, and you just squeeze stuff down. It's sort of like shrink-wrapped execution at every level. And then if you go down to the circuits and the devices, they're just large, large gains there. So for JPEG, encoding, for example, if some of the algorithms that you're using to compress, you could push down into a 10 nanometer device and do it rather than with a software loop running, using more efficiency, you'd get a big speed up. I don't know if that's possible. But so I think that doing what you're describing is a great thing to do, and we should do every bit of that we can. But the big gains, I think, are down in those lower levels where we create a new model and expose it up to a whole new class of languages and application developers. So we should do both, is the answer.
Thank you. Doug, you join us on the boat?
Absolutely.
So any further questions? Find Doug on the boat. Let's go sailing. Thank you very much.
Okay. Thank you so much.
Thanks, Doug.